Okay. So we've already got the ideal gas law up here. So we've already derived it. Usually we give this to you kind of the other way around. We start with Charles' law and Boyle's law and Avogadro's principle, and then we use those to kind of bring this about. I'm going to take this backwards. I'm going to assume you guys have already seen this, and we're going to kind of go the other way around. So how many variables are there in the ideal gas law? There are 4. They're not 5. Why are there not 5? R is a constant. So he's a constant. The rest are variables, though. So all the relationships we can look at are comparing 2 things at a time. And I can compare any 2 variables at a time, provided I'm keeping the other 2 constant. So let's say I assume I keep everything constant besides P and V. So I keep N constant and T constant. R already is a constant. How are P and V related to each other? Yeah, well, as one goes up, the other goes down. So they're inversely proportional, we say. Inversely proportional. So on the other hand, so what if I compare, say, V and T? Assuming I hold everything else constant besides volume and temperature, how would volume and temperature be related? They're directly proportional. If I make V larger, then T's got to go up as well to maintain the equality. So here's the way this works. There's no denominator in this equation as it's written, right? So if any 2 variables are on the same side of the equation, they're inversely proportional. If any 2 variables are on opposite sides of the equation, they're directly proportional. So, and now we can pretty much look at any relationship of any 2 variables. If I said, what's the relationship between moles of gas and temperature? What would it be? They're inverse, because they're on the same side of the equation. Hold everything else constant but those 2, and they're inversely related. Great. That's kind of how it works. So the specific relationships we are going to look at here. So all the relationships we'll look at involve volume. So we'll look at Boyle's law, we'll look at Charles' law, and we'll look at Avogadro's principle. And so notice, how many different variables can I compare V to using this equation? Well, V is one of them, so how many are left? 3. And that's these 3 relationships. Each one compared volume to something. What did Boyle compare volume to? Pressure. So, and in this case, Boyle's law says that P times V equals a constant, or at least that's one way to write it. So notice, if we keep everything else constant besides P and V, then P times V would equal a constant times a constant times a constant, which is just a big constant. Hence there. The other way to look at this is if the pressure and volume under one set of conditions equals a constant, and then I change those conditions, just the pressure and volume, then the pressure and volume under those conditions would still equal the same constant, so they must equal each other. And so another way of writing this is that P1 V1 equals P2 V2. Cool. Both of these are ways of expressing Boyle's law. Now, if you look, this is not, Boyle got his name on a law for this. It used to be a lot easier to get your name on a law. I picture Mr. Boyle back in the day in his laboratory with a balloon, like a regular party balloon. And he blows up the balloon. And he ties it off. Now he's got this balloon. And he starts squeezing on this balloon, and squeezing on this balloon, and squeezing on this balloon. And what happens? It pops. And we're like, wow, great. Whereas Mr. Boyle was like, Eureka! I'm a genius! Because as I squeezed on it, the volume went down, causing the pressure to go up, which is why it popped. Put my name on it. Great, Mr. Boyle. We put your name on it. And 200 years later, it's still there. Great. So Charles. Charles compared volume to what? Temperature. And how are volume and temperature related, since they're on opposite sides of the equation here? They're directly proportional. So as one goes up, the other goes up. A couple of different ways you can express that. You could say volume over temperature equals a constant. And so if volume goes up, temperature has to go up to maintain this equality to a constant. Or again, you could compare 2 sets of conditions. V1 over T1 equals V2 over T2 means the same thing. So, and Charles I'll give a little props to. Out of the 3 laws here, Charles is probably the one who had the most kind of ingenuity going on inside his head, at least the most happening. Boyle I'm not too impressed with. So, but Charles if you look at what's going on here, so this is kind of the principle behind a hot air balloon. So let's say you're floating along in a hot air balloon, and 200 yards up the way, you see, oh gosh, we're going to hit power lines. What do you do? And don't say jump. Pull the jet. Why do you pull the jet? So it heats up the gas, and what is heating up the gas giving a higher temperature lead to? But why? What does it directly lead to? Higher temperature leads to higher volume. And in this case, the volume of the balloon expands. There's the same amount of gas inside the balloon, same amount of air inside it, but now it's taking up more volume. And if you look, density equals mass over volume. The mass of air inside the balloon hasn't changed, but the volume is larger, which means what about the density? It's now less dense. And if it's less dense, then the air around it, just like a helium balloon is less dense than the air around it, what has to happen? It has to rise. So same kind of thing going on there. That's Charles' law. I'll give him props. Props to you, Mr. Charles. So, but Mr. Avogadro is kind of the dumbest one of the lot. What's Mr. Avogadro also famous for? So yeah, 1 mole equals 6.02 times 10 to the 23rd. That's Avogadro's number. And guess what he compared volume to? Moles. So in this case, volume and moles are related how? Good. So volume is proportional to moles. That could, not that one. Alpha here could be proportional to. So, or another way to write that is, again, V1 over N1 equals V2 over N2, or to say that V over N equals a constant. Cool. And like I said, Mr. Avogadro is really the dumbest one of the lot. And just like Mr. Boyle, I envision him back in his laboratory way back in the day playing with a regular party balloon. So at least Mr. Boyle had to blow his up, tie it off, and then do something. Mr. Avogadro just blew up the balloon. Took a regular balloon and that's when he got really excited. Eureka! I'm a genius! Holy cow! As I put more moles of gas in the balloon, it gets bigger. Wow, put my name on it. That is Mr. Avogadro, and he has his name on a law or principle to this day, 200 years later. Way to go, Sherlock. So if you combine these three principles, that's where you'll probably explain that's how we derive the ideal gas law. Well, I'm taking advantage of the fact that, again, you've already seen this once, and we'll just go backwards. But you probably should know these three laws by name. So, and it might help if you remember they all involve volume in some way, shape, or form. How else you want to come together, and come up with, BPV, blood pressure valve or something. I don't know. Take your pick. So CTV, so because you can see your TV, I don't know. But come up with a way. You need to know what each of these guys compared volume to. Cool. Can somebody take the ideal gas law and tell me what this would equal according to the ideal gas law? Good. It equals R. So it equals R. So if I had the pressure, volume, number of moles of gas, and temperature under one set of conditions, that ratio would equal R. What if I change those conditions to a second pressure, a second volume, maybe even I changed the moles of gas, added or subtracted, and I changed the temperature? What would this ratio now equal? Also equals R. So if this equals R and this ratio equals R, then what must be true? They equal each other. Anybody remember what law of geometry that was? What property? Good. I would hope not. All right, so if we look, these are equal to each other. This is what's often commonly referred to as the combined gas law. Well, truth be told, the combined gas law you're usually given is without the N1 and the N2. So why would they be able to leave the N1 and the N2 out of the normal combined gas law that's usually given to you? If they were equal. So if you don't add any more moles of gas or subtract out any more moles of gas, great, then you could get what's normally given to you as the combined gas law of P1 V1 over T1 equals P2 V2 over T2. However, there's one time when that doesn't work, when the moles of gas changes. So this one will then work for any variable changing. So notice if the moles of gas are equal, Great, they cancel. So notice if the pressures are equal, great, they cancel. So and so on and so forth. So if any two variables don't change, just cancel them out. They're going to fall right out of there algebraically. So we've got two equations then. So the better combined gas law. So and then you're just playing up ideal gas law that you might be doing calculations with. So and the question becomes is how do you know which one of these you're actually going to be using? Well, it depends on what question you're asked. So notice if I told you that initial volume on a sample of gas is 10 liters. So the initial pressure on a gas is 2 atmospheres. So, and I tell you that the initial temperature is 273 degrees Celsius. And then I tell you that I changed the pressure to 10 atmospheres, and I changed the temperature to 0 degrees Celsius. And the question is, what is the new volume? What do I do? Which equation is relevant here? The first one, the better combined gas law. Why? Awesome. You're given two sets of conditions here. Two sets of conditions is your better combined gas law. If you're only given one set of conditions and asked to solve for something, great, then you're going to use the ideal gas law. So how many variables in this equation again, the ideal gas law? 4. If I want you to solve for one, what I got to give you? The other 3. Awesome. So we'll do an example of that here in a sec. So, but first we're going to do this one. And we're first going to do it in our head. You guys cool with that? You don't look too confident there. So if we look here, so what did we do to the pressure? Increased by what factor? By 5. How is pressure related to volume? Inversely proportional. So if this was the only change I made, let's say, if all I did was increase the pressure by a factor of 5, what would the volume do? It would decrease by a factor of 5. They're inversely proportional, Boyle's law, right? So in this case, it would be 1/5 as much. And so in this case, what would that volume end up being? 2 liters, okay? So assuming that was the only change, that's what we do. Great, but we also changed the temperature. By what factor did we actually change the temperature?
Negative.
Careful. The answer, let's not do this one because you're like 0, how to deal with that. What if I change the temperature from 10 degrees Celsius to 20 degrees Celsius? By what factor did I change it? Don't say double. Anywhere in this chapter, temperature has to be in Kelvin, and that's the key here. And going from 10 degrees Celsius to 20 degrees Celsius, when they give you that set of numbers, want you to double it. But what that really means is you're going from 273 Kelvin to 283 Kelvin to 293 Kelvin. Is that really doubling? No. Notice the Celsius scale. Somewhere, Mr. Celsius just said, water freezes there and boils there. 0, 100, done. He just arbitrarily said that's 0. Is that really 0? If I said, you know what? I'm going to ignore everybody shorter than 5'8" from here on out in the universe. 5'8" is the new 0, and anybody shorter, you don't matter. I know. Sorry, Bree. And so, Thomas, how tall are you, Thomas?
6'3".
No, you're not 6'3". On the new scale, you're 5 inches tall. 5'8" is the new 0. 6'3" is now 5 inches. I can't do math, can I? 7 inches. 7 inches. So that's the new scale. And how tall are you? 5'6". No, sorry, you're -2. You don't really count anymore. Anybody over here taller than 5'8"? Cool, you all don't matter. Sweet, and that's my new universe. I just arbitrarily set a new 0. Is this the real 0 for height? No, just arbitrary, right? So same thing with Mr. Celsius. He just arbitrarily set the freezing point of water as 0. It's not a real 0, but Kelvin has the real 0. And so if something's doubling or tripling or whatever, you can see it on the Kelvin scale. What is 273 degrees Celsius in Kelvin? It's actually 546 Kelvin. You got to add 273 to it. What is 0 degrees Celsius in Kelvin? 273 Kelvin. What did we really do to the temperature? Yeah, it's half as big as it was. How does pressure how does volume relate to temperature? They're directly proportional. And so if the temperature is half as big, then the volume will also be half as big. And now we're ready to go. Notice, I didn't give you anything about the moles of gas, so we can assume it didn't change in this case. In this case, from the pressure alone, we figured out that the pressure being 5 times bigger, the volume is going to be 5 times smaller, 1/5 as much. And from the temperature being half as high in the Kelvin scale, the volume is going to be half as big. Combine these two, and what should happen to your volume then? Should be only 1/10 as big as it was, and now our new volume is going to be 1 liter. We just did it in our head without plugging and chugging. Now, truth be told, we can go right back here and plug and chug this. So what's true about N1 and N2 in this example? Yeah, they're equal. So if N1 equals N2, those cancel, go away, and we're good to go. And if you plug all those numbers back in, and again, temperature has to be in Kelvin, you're good to go. Now, one thing to note, pressure, take your choice on units. If you want to do pressures in atmospheres, great. If you want to do pressures in torrs, great. If you want to use millimeters of mercury, Pascal, whatever. As long as you use the same units on both sides, all of the pressure scales have real zeros, and you're good to go. But temperature, you better make sure, is in Kelvin before you plug anything in this entire chapter. Okay, let's say I gave you the next question, and I told you we had 4 grams of hydrogen gas. The pressure is 380 torr. The temperature is 0 degrees Celsius. And guess what question I'm going to ask you? Good, what's the volume? What's the volume? I gave you 3 out of the 4 variables. And how do I solve this then? Yeah, in this case, with only one set of conditions, we're definitely going to use the ideal gas law. Okay, now I got a problem here. What's R again? 0.08206 what? Liter atmospheres per mole Kelvin. And if I'm going to use that value of R, then I've got to get every one of these: pressure in atmospheres, volume in liters, moles of gas, and temperature in Kelvin. Am I ready to plug and chug yet? Cool, what do I got to do? Well, let's turn grams of hydrogen into moles of hydrogen. How do we do that? Yeah, what is the molar mass of H2? 2 grams. So if 1 mole weighs 2 grams, then 4 grams would be the same as 2 moles. Great. So here we have 2 moles of hydrogen gas. Awesome. And I got to turn torr into what? Got to turn torr into atmospheres. How do I do that? Good. Atmospheres on top, torr on bottom, and 1 atmosphere is the same as 760. And this is the equivalent of 0.5 atmospheres. Okay. Same thing here. Temperature can't be in Celsius. What do I got to do? Add 273, and we find out that we're at 273 Kelvin. And now we're finally ready to plug and chug into the ideal gas law. So if you rearrange, what is V actually equal to? If you rearrange V, the ideal gas law, it's all for V. nRT over P. In this case, N was 2 moles of gas. R, again, is still 0.08206 liter atmospheres per mole Kelvin. Maybe I'll write moles right there. In this case, T is 273. And all over P here of 0.5 atmospheres. And if you look, moles cancels moles, atmospheres cancels atmospheres, Kelvin cancels Kelvin, and I'll be left with an answer in liters. If all the answer choices on a multiple choice test are in milliliters, well then once you get your answer here, you'll have to convert. But we're going to principally solve this out in liters. Anybody get me an answer for this?
I got
89.70? It's actually really close. That I'm going to go with it.
Can we just use 0.0821?
So, and that's why you came off just a hair off what I was going to do. So I actually just, turns out this comes out to 22.4 times 4. So, which gets you really close to that. But yeah, if you use 21 instead of 206, you'll get that. Awesome. Which would be close enough on a multiple choice test. Cool. Cool. So one set of conditions, P equals nRT. Two sets of conditions, combined gas law.